So next we do the example taken from the past year final exam. So this is a cascode amplifier. Cascode amplifier is a direct coupled multi-stage amplifier. So cascode consists of the common emitter plus the common base. So in this cascode amplifier, the two transistor has the similar beta value and VBE. Okay. So and then it's also given the ICQ1 is given as a 2 milliampere. So this is IC1 is 2 milliampere. Okay, we do the first question. First question is a DC analysis. Calculate the approximate value for ICQ2 and collector DC voltage VCQ1 of transistor Q1. Okay. From this circuit, okay, for DC analysis, before we proceed with the calculation, you can remove the bypass here. Sorry, not the bypass, the input as well as this bypass can be removed. Also, this part can be removed. So this is a DC analysis. Okay. So next, we label what is the ICQ2. Sorry, ICQ1 is 2 milliampere. So we want to calculate the ICQ2. Where is ICQ2? ICQ2 is this direction. This is ICQ2. Okay. If you take a look at the emitter of the second transistor Q2, this is your IE2. So you notice that IE2 equal to ICQ1. Okay, IE2 is equal to ICQ1 is equal to 2 milliampere. Okay. So the relationship between IE2 and ICQ. So we can get the relationship because the IE2 is equal to beta plus 1 IB2. And then you know the IB, you want to if you can convert the IB into the IC using the IC over IB equal to IC over beta. So this is beta plus 1, IB2 is equal to ICQ2 over beta. Okay, lastly, you can get this one is beta plus 1 over beta. This is ICQ2. So IE is 2 milli. This is 2 milli. And beta is 200. So 201 over 200 is ICQ2. So we can determine the ICQ2 equal to almost similar to the IC1. Okay, so this is the answer for the ICQ2. So next we can calculate the VCQ1. So VCQ1. Okay. For the VCQ1 is here. This is VCQ1. So how we can analyze the VCQ1 is by using the KVL here. Okay, KVL that passing through the base emitter of the Q2 as well as collector emitter for the Q1. So this you want to do the KVL here. So if you want to do the KVL, you need to simplify the RB4 and RB3 here. Okay. So RB4 and RB3 here is actually a voltage divider. Okay, apply 12 volt voltage division between RB4 and RB3. So we need to do the Thevenin theorem. So the R Thevenin equal to RB3 parallel with RB4. So this is equal to 10k parallel with 10k equal to 5 kilo ohm. And then V Thevenin is 10k over 10k plus 10k times the source is VCC is 12. This is equal to 6 volt. Okay, so if I redraw this part, so at the Q2, so this is the V Thevenin and this is the R Thevenin. V Thevenin, R Thevenin. And then this is Q2. This is the Q1. Okay, this is RE. This is RE, This is the RE. Okay. So the point here, we want to calculate the VCQ1. Okay. So our KVL, we start from the VTH and then the R Thevenin, VBE, and end at the VCQ1. So the KVL equation will be the V Thevenin is 6, so minus 6 plus the voltage drop at the R Thevenin. This is the IB2. IB2 is equal to, we know the ICQ is 2 milliampere. So IB2 is equal to 2 milli divided by the beta. Beta is 200. So this IB times the R Thevenin is 5k. And then plus the VBE here. VBE is 0.7. So plus the VCQ1 equal to 0. So the VCQ1 equal to 6 minus this one is 0.05 volt minus 0.7 equal to 5.25 volt. So this is the solution for the VCQ1. So next question, the second question, draw the small signal hybrid pi AC equivalent circuit at the mid band or middle frequency. Okay, so as usual, capacitor is short circuit. So short circuit, so RE is removed. Short circuit, RB3 and RB4 is removed. So you'll get, this is your VS here. Okay, this is your RS. And then we have the RB1 and RB2. RB1 parallel with the RB2. Okay, between the base and emitter, we have the R pi 1 and the emitter is grounded. This is the R pi 1. Okay, between the base and collector, between the emitter and collector, we have the, so this is G1, GM1 V pi 1. V pi 1 is here. Okay, and then we have the collector is directly connected to the emitter. So now the Q2 is the NPN. This is NPN. So the NPN, the current direction is here. Current direction is here. So this is the, between base and emitter we have the R pi 2, and the voltage V pi 2. The polarity of V pi 2 is here. So we have, because the current flow upward, so the positive will be at the down. So, and then the GM2 V pi 2 current source direction will also is pointed to the left hand side. So at the collector, you have the RC, and lastly we have the RL. Okay, so this is the small signal hybrid pi AC equivalent circuit at the midband. Okay, so so next the third question is calculate the small signal voltage gain. So we have three different voltage gain, V out over VI, VL over V out 1, VL over VS. So VL is voltage drop at the RL, V out 1 is the voltage drop at the output port of the first stage, VI is the voltage at the input port. Okay, for the first question, V out 1 over VI. So what is V out 1? So V out 1 for V out 1 is the voltage. So where is the V out 1? So this is V out 1. So V out 1 is the voltage across the this R pi 2, across the R pi 2. So if we denote the input impedance of the second stage as ZI2, so the voltage V out 1 is equal to minus GM1 V pi 1 times the ZI2. What is GM1? GM1 is equal to IC. GM1 equal to the IC current is 2 milliampere. So this is 2 milli over 26 milli. So the transconductance of the Q1 is 76.92 milli. So this value is also equal to GM2 is also equal to 76.92 milli Siemens, because we have the same, almost the same current, IC current. So for the R pi 1 is equal to R pi 2 because the beta is also the same. So this is 200 over 76.92 milli. So this is equal to 2.6K. Okay, we go back to the V out 1. So the V out 1 is minus GM1 V pi 1 ZI2. So what is ZI2? ZI2 is the impedance is equal to the impedance seen from the emitter. This is the ZE. So we know the ZE is equal to R pi 2 over beta 2 plus 1. Okay, so this is minus GM1 is minus 76.92 milli. So this is V pi 1. ZI2 is equal to R pi 2 is 2.6K over beta 2. Beta 2 is 200 plus 1. So this will give the minus 0.99 V pi 1. Okay. And then what is the VI? VI is equal to V pi 1. So this is the V pi 1. So VI is equal to V pi 1. So this will give the V out 1 over the VI is equal to minus 0.99. Okay. So next one is the VL over V out 1. VL over V out 1. So VL is equal to the minus GM2 V pi 2 RC parallel with RL. So this is minus 76.92 milli V pi 2. RC is 2K, RL is 10K. 10K. So this will give you minus 128.46 V pi 2. So next we express the V out 1. So in the calculation of V out 1 over VI, we express V out 1 as a function of V pi 1. So now we want to express the V out 1 as a function of V pi 2. So what is the V pi 2? V pi 2 is the polarity. This is the polarity of V pi 2. So V out 1 is equal to minus V pi 2. Okay. So this will give the VL over V out 1 equal to 128.46. The value will be positive because the negative is cancelled out. So the last again that we want to calculate is VL over VS. So VL over VS is actually VL over V out 1 times V out 1 over VI times VI over VS. So VL over V out 1 is equal to 128.46 and V out 1 over VI is equal to negative 0.99. So what is VI over VS? VI over VS is a voltage division between the input impedance, the ZI plus RS. So what is ZI? This is your ZI. ZI is equal to RB1 parallel with RB2 parallel with R pi 1. So here the ZI equal to RB1. RB1 is 33K parallel with RB2 is 10K. R pi is 2.6K. So this is the 1.9 kilo ohm. So VL over VS is equal to 128.46 times minus 0.99 times 1.9K over 1.9K plus the RS is 100 ohm. So this is 0.1K. So the answer is minus 120.8. Okay, so this is the final answer. Okay, from this analysis, this is cascode multi-stage, this cascode amplifier. So what we can conclude from our calculation. First, regarding the voltage gain. So voltage gain is, the AVS is minus 120.8. So this is quite high. Okay, can consider it relatively high voltage gain. So cascode has high voltage gain. How about the input impedance? The input impedance is we have calculated here. The input impedance is 1.9K. So this is 2K. So this is not a very high input impedance, but if you compare with the input impedance of the second stage, the input impedance of second stage is much lower. So this is ZI2 is 2.6K over 201. So this is around, it's not around, it's less, it is 12.9 ohm. So actually ZI2 is equal to 12 ohm. So we can, this is a moderate value. So 1.9K. Okay. So and then another thing is, if you see the AV1. So this is AV1, the voltage gain for the common emitter. The voltage gain is minus 0.99. So this is close to unity. Unity means close to 1. So minus 0.11. So close to 1. So why this is important? Because when the AV is close to 1, the CMI is equal to 1 minus 1 1 CBC, and this will get you 2 CBC. So this will give you a very the effective capacitance at the input side is the double of the feedback capacitance, but still it is lower than the single stage of common emitter. So this is quite low. This is low, and then the FH is inversely proportional to the CMI. So the low CMI will have the high cutoff frequency. So this will give the high cutoff frequency. Or we can or another way to describe it as a wide bandwidth. Okay. So this is the conclusion that we can make based on our calculation for this example.